Now we are going to further discuss Fischer projections. So this is what we did when we set up Fischer projection. The most oxidized group at the top, the aldehyde keto group. Carbon atoms are at the intersection of vertical and horizontal lines, and the H and OH groups on the horizontal intersecting line, they are set up on the horizontal lines, the H and OH, places the CH2OH at the bottom of the Fischer projection, which is not chiral. So let us see. We're reviewing the chiral carbon furthest from the carbonyl group determines the L or D isomer. Left is assigned L, D, right is assigned D. So we are identifying D and L. Monosaccharides. So now I'm going to see what is this molecule. 1, 2, 3, 4, 5 carbons. These are the chiral carbons. These are the 3 chiral carbons. This is the carbonyl group, and we are going down for this to the carbonyl group, sorry, the carbon atom that is chiral. This is not a chiral carbon atom. This is the last chiral carbon atom coming down from the carbonyl group. So in this carbon, the OH, so this is the chiral atom, carbon atom furthest away from the carbonyl group. OH to the left, L. Carbon atom furthest from the carbonyl group. OH to the right, D. This is a glucose molecule. You can see there are 6 carbons, 1, 2, 3, 4, 5, 6. The molecular formula is C6H12O6. So there are 6 carbons. This is the carbonyl group. This is the carbon that is chiral furthest away from the carbonyl group, D, L. So D glucose, L glucose. So if you see the terms, now you know what it means. How do you identify a D and L? So in the following Fischer projection of mannose, identify the monosaccharide as a D or a L. So I'm going to go up here, look at the carbonyl group, go down. First chiral carbon, second chiral carbon, third chiral, the last chiral carbon, OH to the right, it's a D isomer. So this is how you analyze the problem. Identify the carbon chain, the chiral carbon, position of OH. 5, OH is drawn on the right, carbon number 5, which makes it D mannose. This is the mannose, D. The OH group on the chiral is drawn on the opposite side. So when you are in the L, you have a mirror image. The OH is on the opposite side. There. Now, in the following, identify the number of chiral centers. Identify the monosaccharide as a D or a L. Now, identify the number of chiral centers. How many chiral atoms are present? This is a carbonyl group. It does not have, this carbon does not have 4 different groups attached to it. It has 1, 2, 3. So we cannot determine chiral, achiral with this carbon. It does not have 4 groups. This is the first chiral carbon that we see. 1, 2, 3, 4 different groups. This is a group here attached. This is the second carbon that's chiral. 1, 2, 3, 4. This is again achiral. This carbon is attached to OH and 2 hydrogens. So this is achiral. So there are 2 carbons that are chiral in this molecule. Identify the monosaccharide as D or L. So I am carbonyl going furthest away to the furthest away carbon atom that's chiral, OH to the left, L isomer. So let us see. 2 chiral centers, OH on the left is a L isomer. glucose and fructose. So the glucose and fructose both are monosaccharides. So fruits, corn syrup, honey is the aldohexose. We know what that means. Hex, it has 6 carbon chain, has an aldehyde group, is a carbohydrate, and the formula is C6H12O6. It's also known as dextrose and blood sugar in the body, a building block of sucrose, lactose, maltose, cellulose, glycogen. Glucose is a very important building block. It's a monosaccharide. It's a one unit. So it builds into larger molecules. Fructose is obtained from sucrose, is a ketohexose. We know what that means. Has a keto group. The second carbon has a keto group, 6 carbon chain. The molecular formula is the same. Aldohexose, ketohexose. The sweetest is twice as sweet as sucrose. Sucrose is table sugar. So a table sugar molecule, sucrose, is a disaccharide. It has a fructose and a glucose unit together. Disaccharide, 2 units of monosaccharides. So this is honey, and the sweet taste of honey comes from the monosaccharides D-glucose, D-fructose. So we know D, OH to the right. So this is a good time to look at glucose and fructose. See, aldo, keto, aldohexose, ketohexose, D, D-glucose, D-fructose. Galactose. Galactose is another monosaccharide, C6H12O6, the same molecular formula. So you can see this is the aldehyde group, D, OH, H, OH to the right. So is it aldohexose? Is not found free in nature, is obtained from disaccharide lactose. Lactose is a disaccharide. Lactose is a carbohydrate in milk. So by the hydrolysis of carbohydrate, what is hydrolysis of a disaccharide? Is breaking down into the individual units. Has a similar structure to glucose except the OH in carbon 4. So 1, 2, 3, this OH, the position of this OH in galactose is different than glucose, and that's the only difference it has from a glucose molecule. In a condition called galactosemia, an enzyme needed to convert the galactose to glucose is missing. So galactose, this is again a monosaccharide obtained from lactose. Glucose, a glucose tolerance test, blood sugar, ingesting glucose. So this is about hyperglycemia, hypoglycemia, normal blood sugar levels. Okay? So there is a graph that talks about hyper, hypo, and normal blood sugar level. So that is connecting glucose to our health. Diabetes can cause hyperglycemia when the pancreas are unable to produce sufficient quantities of insulin. Insulin is an enzyme, allows glucose levels in the body fluids to rise as high as 350 milligrams. Symptoms, these are your symptoms, and some of the, reasons, one of the many risk factors. This is hyperglycemia, when the blood sugar levels are higher because the pancreas do not produce enough insulin. Hypo and decreases rapidly. Now, this results by the overproduction of insulin, the enzyme. What does the insulin do? It takes the sugar from the blood and deposits into the different muscles and all the different areas where the need is. Symptoms may have dizziness, general weakness, muscle tremors. So this is a management of hypoglycemia, high protein, small amounts, low in carbohydrate. So this is your chemistry linked to health. We're discussing diabetes, generally what it means, hypoglycemia. Draw the Fischer projection of D fructose, L fructose. Again, fructose is a keto hexose. So we have a keto group, 6 carbons in a chain. So let us see. Keto group, the second carbon has the keto group. Second carbon, 6 carbon chain. 1, 2, 3, 4, 5, 6. Now, starting from the carbonyl group, I go to the furthest carbon, that is chiral, OH to the right, D fructose, OH to the left, L fructose. Okay. For today, and then I'll see. Let me finish, and then I'll talk. Oops. Okay. Now we are going to discuss the Hayward structures of monosaccharides. We just discussed the Fischer projections and how to determine the D and the L enantiomer. Now we are going to talk about Hayward structure, and this is what a Hayward structure looks like. So we are going to, the goal will be to draw and identify Hayward structures of monosaccharides. So we discussed pentose sugars, hexose sugars. These are the most stable forms. The Fischer projections, the open forms that we saw in Fischer projections, and these cyclic forms that we see in Hayward. So the most stable are the ring forms of the carbohydrates. These rings, known as Hayward structures, are produced from the reaction of carbonyl group and hydroxyl in the same molecule. So when we lay out these molecules as Fischer projections, they are the open structures. These are the ring structures, and the ring structures are more stable. So we will learn how to draw these structures from the Fischer projection. How do we get to the Hayward? That is the next step. And here you see that the carbonyl group and the hydroxyl in the same molecule are connected. So we'll see how that works out. Guide. Turn the Fischer projection clockwise by 90 degrees. Fold the horizontal carbon chain into a hexagon and bond the oxygen on carbon 5 to the carbonyl group. Draw the new OH group on carbon 1 below the ring to give the isomer an alpha, or above the ring to give the beta. Alpha and beta, or beta, I say that beta. So alpha, beta isomer. So let us see. This is the Fischer projection. Step 1, we are going to turn the Fischer projection 90 degrees. Okay? So that's what we are going to do, turn it 90 degrees. And now this is carbon 1, 2, 3, 4, 5. This is your carbon 5. This is the oxygen. Okay? This is carbon 6. This is your open chain. We are turning it 90 degrees. That is step 1. Okay? Fold clockwise to make a hexagon and bond the oxygen on carbon 5 to the carbonyl. So we are turning it clockwise, and this O bonds to this carbon and the H to the oxygen. Okay? So we are taking carbon 5 and moving into a hexagon and bringing it this end, this oxygen from carbon 5 bonds with carbon 1, and the hydrogen in the hydroxyl connects to the oxygen to set up a hydroxyl group. This becomes a hydroxyl. So this is the carbon 1 with the carbonyl group, carbon 2, 3, 4, 5. And this is your 6 carbon, and this is where the oxygen is connecting the ring. So this is the new cyclic structure. Okay? So this is the Hayward structure. Place the carbon 6 group in the CH2OH group above carbon 5. Draw a bond between the oxygen of the OH group on carbon 5 to the carbonyl. So oxygen to carbonyl, draw a bond. Okay? And the hydrogen from here is connecting to the oxygen here. So this is step 2. So place carbon 6 group in the CH2OH group above carbon 5. So this is how your CH2OH has lined up above carbon 5. Now, when we are setting up the alpha or beta isomer in Hayward structure, the position of the OH determines an alpha or beta in the Hayward structure. So when the new OH group on carbon 1 below the ring to give the alpha isomer, below the ring, the new hydroxyl group above the ring, beta isomer, beta D glucose, alpha D glucose, beta D glucose. So we had started off with the D glucose. D is to the right. Okay? So we started off with the D glucose, and we have folded the open structure to create an alpha. Alpha, the OH is below the ring. Beta, the OH is above the ring. Okay? So now, when placed in a solution, so when you have this sugar molecule in a solution, what is a solution? A solution is a homogeneous mixture. You have the sugar molecule with a solvent having a uniform mixture, so it is called a solution. Now, when you have a glucose isomer in a solution, it says 36%, that is the mass percent of a solution. So now when you have this alpha isomer, alpha D glucose, you have it in a solution, you have an open chain, then you have a beta glucose. So there is a alternation between the alpha opening up, closing the ring as a beta. So when you have these ring structures in a solution, there is a rotation between the alpha and the beta. There is a mixture of alpha and beta in that solution. So in a solution of alpha D glucose, in a solution we'll have 36% will be the alpha, 64% will be the beta isomer, and it will open and rotate into beta, open, rotate into alpha. You can see there are arrows pointing in both directions. This tells you that the reaction moves forward and then moves backward. So you have a isomer alpha D glucose in a solution. In a solution, this ring will open into an open chain, close again into beta, open, come back. So this is a dynamic reaction. And finally, when the reaction has set into equilibrium, you will have 36% of alpha and 64% of the beta glucose. So that is mutar rotation of alpha and beta D glucose. Okay? So now we are in fructose, the Hayward structure of fructose. Again, fructose is a ketohexose, and we'll repeat the same process with ketose. So this is a ketohexose. It forms a 5-carbon ring because when we are closing with carbon 2. So forms when the OH group on carbon 5 reacts with the carbon 2 in the carbonyl group here. So we are going to rotate it 90 degrees, fold it so that the OH, the O bond to carbon 1. Okay. So this is your alpha D fructose. So this is your alpha below the ring. There is your beta above the ring. So here the two CH2OH, they are lined up. This is the CH2OH here, and this is the CH2OH here. There are two CH2OH in fructose. So when you're folding this molecule and connecting it here, this will line up here, and this determines alpha or beta. And this O connects to this carbon, and this H goes with the O to create the hydroxyl group. And this hydroxyl group, the H and the O, that determines if it is alpha or beta fructose. But the difference between glucose and fructose, it forms a 5-atom ring structure with carbon 2. Write the cyclic form of D-galactose. So let us see, this is galactose again. Galactose and glucose differ in the OH group, carbon 4. In glucose, the OH is on the right side. In galactose, it's on the left side. This is D-galactose. The carbon furthest away from the carbonyl group has the OH to the right, D-galactose. So what we will do is first we will rotate 90 degrees. So there is D-galactose. We are rotating D-galactose. Now we are going to fold the carbon. The OH connects, the O from the OH connects to the carbon. The hydrogen connects to this oxygen. So 90 degrees. Now we are folding. So now we fold this O connects to the carbon. We draw a bond. The OH connects to the, not the OH, but the O connects to the C, H connects to the O. So place the carbon 6 above the ring. This is carbon 6. Write the OH group on carbon 2 below the ring, and the OH group on carbon 3 and 4 above the ring. So that's where you set up a galactose molecule. This is your alpha isomer. This is your beta isomer. Draw the new OH group on carbon 1 below the ring to give the alpha and above the ring to give the beta isomer. So this is, right, 2, 3, 4. Place the curve above, write the OH group carbon 2 below and the carbon 3 and 4 above the ring, and that's what we did, above the ring. And that's where we have a galactose, beta alpha D galactose.